Sorry, you know, you mean not perfect. All right, now I'm recording. All right. Today we talk about the emergent FA, and we'll review a little bit FA we covered earlier. And this is a CSE 460, and I plan to post this talk, this class, onto the YouTube so that other people can watch that too, because it's something that will be useful for others. All right. And for FA, the feature is that we have a state marked by, say, Q. Then you probably have a input A, and you go to another state. Then you have another input B, you go another state, all right? So that give on the Q prime, Q double prime. And they are different. For each A, you have a unique target, all right? And you have a B input, you have a unique target, Q double prime. And that's our FA, finite automata, in our course. And in electrical engineering, we also call it finite state machine. Some people write it as FSA, S for state, all right? And we cover NFA, non-deterministic, right? Non-deterministic. That's for that N. And that's the subject we covered a little bit last time, but we almost start from scratch. And that's actually, Brain does that actually. Brain is very much a non-deterministic FA, but we'll see what happens, all right? So suppose I have a state Q, and I may have A, then you have a Q prime, and I have the same A, I may go to Q double prime, right? And another state in general case that it could be like, so you first state Q, 1, 2, 3, then you probably, I would say this one, you have a B. So non-deterministic means that from a state Q, you have the same inputs A, you may lead to 2 different states. That's the first mechanism. The second mechanism is that we have lambda transition. Lambda transitions is like that. I have a state, I may have a Q, but without consuming input, I can go to another state, Q prime. You know, without even take any input. Lambda means empty string. But you can think about that this is just a different way of writing it, because here you don't have lambda, but this lambda transition means that you can reach Q and you can reach Q prime too. Over here, you reach Q prime and Q double prime with A input, but with this lambda is like you can, example that A, then the lambda transition, then A lambda, you can reach to this one, and without lambda transition, you can just use A. You can see that. So this one is very much like this, but sometimes this is convenient, all right? Lambda transition is convenient. So let's do definition. Definition, NFA, right? NFA has a delta transition, others are the same. State, then you have a alphabet, sigma, but now alphabet allows this lambda, which is empty string, just just no letters. That one expanded, so this is expanded. So state, this one goes this one, and this is a transition will go to, originally it's a Q, state Q. But now it's a subset of a state Q. That's what we said, all the possible subsets of Q. Example, here we have 2 states of that Q. Then 2 is a subset of Q, all right? Here only one, so it's a simple case, but in general, you can have 2 states, you can have 3 states, you can have 4 states. So those are the subsets, all right? Subsets of Q, that's called a power set. That's what we learned, all right? And I'd like to discuss what do you mean by acceptance. NFA acceptance. We have at least, you have a string starting with the initial state, and you reach at least one accepting state. At least one accepting state is reached. Then the entire string is accepted. The entire string that you scan so far. So in other words, it don't care of other states that's not accepting state, as long as reach one, that's good enough. 2, same thing, you accept it, all right? So very intuitive. So now instead of one trajectory from a strings, you have multiple trajectory. And so there are more cases. And then as long as one trajectory is on the accepting state, the entire string is accepted, all right? And there is a method that convert from NFA to FA. Given any NFA, you can construct another machine called FA that accepts exactly the same set of language, all right? So NFA did not really increase the power. So let's look at example. Suppose that I write an example how you do it, all right? Not very difficult. So suppose I have a state 0, double circle, accepting. I have state 1, and I have a state 3, double circle. Then I have state 2, single circle. Then you have a A, you have a A, and maybe sometimes the same A, B, sometimes single arrow, but we just use both, basically the same. All right, that's A, and then that's A. All right, and where's B? From here, B is gone. All right, B is gone means that it's rejected, basically. It's called crash. You start from, you start with B, it's rejected. Once you reject it, then there's no path to go on, all right? So that's, then here you start with A and B. I don't draw it because it crashed, all right? So I write a simple FA like this, and this is called NFA, and the set of accepting state is 3, all right? Oh, wait a minute, and 0. 3 and 0, right? 3 and 0. We have a double circle, all right? So now, then they convert that one to FA. I just start with the simple we already have, all right? Suppose I have a FA, this is M1, all right? This is M1, and we construct M2. The M2 is FA. M1 is NFA, right? And I'd like to start with a transition table so you can see how it goes, right? And from here, you want to have a state you reach. This is a subset. All the state here is a subset. Currently only 0. All right, I'm at 0. Then I have a, so I have a delta QA. I have a delta QB. Then with A, you reach 1 and 2. Now, very important, don't miss anything. From A, you can reach 1 and 2. So that's a subset of Q. Very important. 1 and 2, because reach now 1 and 2. And that is the new state for the FA. Right? And if I have a B, there's nothing. So I going to reach an empty state. But empty state is a state, right? So you give example, empty state, if you on empty state, you have A, you still reach empty state, you have a B, still reach empty. So this is like the last line in the transition table of the new FA, all right? Because empty state is a subset of Q, right? Then you have this one, I put here, I put here that like 1 and 2. Then I have a 1 with A, I reach 1, the A, right? I reach 1. And with 1 with A, I also reach 2. I reach 2. And with 1 with A, I'll reach 3. All right? Can I go to anywhere? I cannot go to 0. Right? So 1, 2, 3 from here you can all reach. So this becomes a new state. That's a subset. So 1, 2, 3 is a new state. All right. Then once you create new state, you want to write here 1, 2, 3. All right. Then with B, 1 with B, I reach 3. All right. And 1 reach B go to 3, and 2 with B going nowhere. So it will not be able to add element into this subset. And if I start from 3 with B going nowhere, all right? So I end up with only 1 state. That's a subset, all right? Not a single state, but rather a subset of Q that consists only 1 state, all right? So that's 3 need to be put here. You keep growing until you are done, all right? Keep growing. So start with 3, all right? Then 1, 2, 3. All the new state need to put here. Don't miss it, all right? Then 1, 2, 3 with A. 1 with A is already the 1, 2, 3. We already know that. 1 from 1 is already 1, 2, 3. So 1, 2, 3. And you can see start from 2, you did not add anything. Start with 3, did not add anything, still have it. So it's like from here with A, you get this, right? Then 1, 2, 3, I use B. 1 with B go to 3, right? And 2 with B going nowhere. 3 with B going nowhere. So I still get that state. You see that? So now these are the same here. I don't need to add a new state. So from 3 with A, you get no, nothing. 3 with B are going nowhere. Haha. So this one's already there. Normally you will have more state, all right? Typically you have more state, but in our case, no, you don't need it. So we are done. We are done without that line, all right? Normally you may have more lines, all right? And today I construct a simple machine. So we have only 1, 2, 3, 4, 5. 5 rows. So we have a FA. Any questions? Any questions? So basically we are tracking all the states has reached. Then all the state reached can be 1, 2, 3, can be 3 or more. And we put a subset as the label for the corresponding state. Then we add a new label, those labels as a subset to the new state until we account all the transitions. We're done, right? Make sense? So very intuitive, very intuitive. And I like this idea. The idea is beautiful, right? Beautiful. And I will explain to you later on that brain does that, right? Brain has a multiple muscle filing, all right? If you consider each muscle as a state, and you have multiple muscle filing, it's like my vocal tract, all right? Vocal tract right now is filing like crazy. Multiple neurons are firing and are making noise, right? So now we have accepting state A. What's accepting state A? I would say this F1 and I was 2 is 2, transition 2. So A2 for machine 2 is as long as it has 0 and 1, right? So 0 is accepting state, all right? So 0 is accepting state. And originally 0, no other state. Then originally 3 is accepting state because as long as it reach 0 is accepting, or you reach 3 is accepting. So now that this is accepting, all right? This is accepting, basically same, all right? So 1, 2, 3 is accepting state, right? All right. Anybody, please help me. Do I miss another one or I'm done? All the accepting state is already taken into account in the F2, machine 2. Anybody? Did I miss any for A2, accepting state? You want to look at
3.
What's that?
3.
3. Thank you. Help me. See that? All right. Now I closed it. Do I miss anything else? What about 1, 2? No. 1, 2 does not include that double circle. All right? All right. So this one accepting, this is not, this accepting, this accepting. What about the empty set? No. Empty set is rejecting. All right. So now draw. All right, we draw. Draw F2. Machine 2, M2. All right. So you draw that way. We say 0 is a state. Then double circle it. Then with A, we go to 1, 2. So 1, 2 is the label of the state. I use circle. Now it's a little bit fatter because the label is bigger. And with A, go to 1, 2. And with delta 2, we have a B, go to empty set, right? So with B, I go to empty set. You see that? That's a label, that's a set, all right? And that one is there, all right? So you can see this is the state. Then I go to with 1, 2 with A, I go to 1, 2, 3. So 1, 2, 3. That's my state, fatter because this is larger, but still a single label. This is considered one single label, all right? And this is supposed to double circle. All right. Then I have, suppose I have this is like A, right? Okay, now this one with B, I go to 3. So B, I will go to 3. That's a subset. And a single circle or double circle. No, double circle. All right, that's double circle because that's the one. All right. Then from here, all right, from here 1, 2, 3, and with A go to yourself. So go to yourself, and with B go to 3. All right, do you see that? And did I miss any? Anybody? Anybody? Is that complete?
No, you missed transitions from the empty state.
Yeah, thank you. We missed. You always do this. For every state, you look at the transition A, B, A, B, A, B, A, B. Ah, this one I missed it, right? So with this one, we'll hit A and B go to the same place. Thank you. A and B. All right. And did I miss anything? check.
The set 3
Yeah, 3
doesn't have
goes
any
where?
transitions. Yeah.
Yes, 3 go to empty set. Yes, very good. All right. So you need to do this one, A and B. All right. Did I miss any? I think it's okay now. All right. So we are done. All right. So we learned how to construct from FA to NFA to FA. So you can, from this example, you can see that it's equivalent. But if you want to prove it, it's not difficult, all right? You just use a notation. Notation is any set here becomes, use a subset notation. And the textbook has proof, all right? Proof. And we don't need to really talk about it here because it's easier to learn that way, all right? Now we move to new section. New section is called, I write a new section, all right? And you will not learn that anywhere on this planet. I think I'm confident nobody will teach EFA because that's our MSU stuff, all right? And I think that's a holy grail. Grail. What do you mean holy grail? Most desirable stuff, a very desirable stuff. That's a story in Bible, all right? It's holy grail. And why is holy grail? The EFA will bridge the gap. I'll write it down, all right? Bridge, bridge the huge gap between the symbolic school and connectionist school, and the connectionist school. School in AI. It's like you have two schools, they are fighting. They said the symbolic school is better, and so far all we are doing is symbolic, all right? We have symbols. And we have connectionist. What do we mean by connectionist? Neural networks, all right? This means symbols. We are so far, computer science is symbols, all right? Connectionist school is about the brain, all right? It talks about neural networks. And this is a huge gap. This is a huge gap. It's like religion. You know, two schools, they fight each other. When I was at UIUC, like 1985, oh, it's a war, religious war. And they say that we're doing better, you're doing better. And I say, hey, guys, calm down. Now, there's a common story about the EFA and get the best of the both worlds, right? And if I say that, and many people will throw egg at me, actually. People say, no, you're doing bragging, right? People just ignore me right now, right? So E is called emergent, or emerge for verb, all right? What do we emerge? Because the FA will emerge, right? And further, when it emerges, its skull closed. Skull is the bone on your head, and it's closed. Closed means that you can construct FA without using symbol. Then you construct EFA in your brain. The brain is skull closed, means that everything inside is automatic. From your infant time to your baby time, to your adolescence time, to your college time, to your adult time, all the way, totally skull closed. This means that auto-programming for general purposes. I will reach that one, all right? This means that autonomous programming for general purposes. And I use an acronym called APFGP. And you have not heard that one. This is pretty new, all right? APFGP. And for the on option, I have a assignment for those who can program yourself to generate FA on the fly using vector input, all right? So basically, it's a general purpose. And I will talk about later that EFA can be moved onto emergent Turing machine. That TM means Turing machine. We learn that later, all right? Turing machine. And that's how it becomes general purpose. Right now, it's not purpose. It's not general purpose. This is like teasing you. Oh, there is something exciting coming up. So don't look down upon this little guy. This one is a monster. Turing machine is a monster. And little guy look like a duckling, but it turns out to be a swan, right? So Turing machine will do that. So this is another class, all right, in this class. So I think that you are fortunate to be in this class. And I understand that this is a subject is difficult. And I talked to TA Jamie, said that you're doing very well in the last two homework. And I talked to Jamie, and I really like Jamie. And he said, let's do another homework session. And I said, I loved it, all right? And I really appreciate it. Right? Work with him, because if you pay a lot of tuition, go to other schools, no matter how expensive that is, you will not learn that, all right? Will not. Especially they just ignore us, all right? So keep that in mind, all right? Now, I move on. So what's the FA? FA, we want to do symbolic. That's old school, right? Good old-fashioned AI, all right? Symbolic match, all right? And suppose symbolic match, suppose I have an A, and I have an A here. And they look different. We see that this one's leg is longer, this is thinner, this is fatter, right? You say same. Same, why? Because you are human. But if I take a picture of that two images, they are different. This is different. So same is we human look at it, because your brain already learned, all right? So this distance is 0. So distance equal to 0. Suppose I have another A and B here. You say, oh, not the same. Not the same. Distance is very, very just different, all right? I'll give another example. Pay attention to this concept, all right? Something that looks trivial is not really trivial, because there is a gold in there, right? And now, I suppose I have a C and a D, all right? And the C really means boot. D means reboot. And you say not the same, right? You say not the same, right? But here, not the same. If I do not tell you the meaning of A and B, they're just not the same. So distance like 1. And if I have C and D, the distance is boot and reboot, they are similar. Maybe the distance is maybe half, 0.5, right? So if I do symbol A, B, C, D, I never know this dimension, the meaning of boot and reboot. So boot and reboot are similar because it looks similar or meaning are similar. But if I just hit A and B on a C and D without meaning, I don't know the distance. And brain is beautiful to see this difference. All right, you say, oh, John, you are same John, and you like the A. I treat the same because I'm in college. You know, maybe maybe your little sister in kindergarten do not treat they are different. All right, they are different. All right, and you say no, it's the same, baby. You are the same, and the baby says no, they are different. And you say, oh, you are just baby, all right? If you go to school and you learn they're the same. But brain is beautiful, but brain knows the difference and will treat different things differently. And so this is the distance. And in symbolic AI, they use distance. And that distance is so bad. There are many, many different distance bad. All right, why? They did not understand these symbols are bad. All right, so it's like a God, you know, God in AR, in computer science, you cannot go over the God, all right? So now we go beyond. So we say, do not use symbols. And this is not new. You know, people say, I don't use symbols, I use emergent. That's my concept, all right? Many people don't call it emergent. I use emergent images. And what do you mean emergent images? And for this kind of symbol, you really have to have a machine or human to be in the loop. So you generate something like ASCII, all right? A, B, C, D, you have ASCII symbols. They different A will go the same ASCII A, different B will go the same ASCII B. But once you have image, they're all different, all right? You always never see the image exactly the same. So I would say that you have an image in your retina, in your eye, and you have images in your cochlea. Cochlea is the place where you have a hair cell, you hear sound, all right? The hair cell will vibrate with this. You hear my voice and your hair cell in the cochlea start to vibrate. It's like image, right? And you have images in your muscle. What do you mean muscle? Because muscle has called neurons, they called spindle neurons. And the neuron will vibrate, then start to contract the muscle. When I speak, many muscles start to contract, all right? And this one is you can have you have images inside the skull, inside your brain. So now, this one I will post later on, I will call it input, right? Input to our FA. And this one will corresponding to our state. And that will have something which I call Y. Y is the neuron in your brain, all right? So that we are later on called X, and this is called Z, and this will called Y. They do later, all right? I'll give you just something to give you impression. All right, any questions? Then you say, how can link the images to symbols? And we start to use calculus, all right, in vectors, right? We use vectors we learned in calculus, and we just suppose I have a vector A, right? That vector has A1, A2, we learned it, right? The beauty of vector is that they have many, many values, not just single value, all right? Suppose I have image, I suppose image, and that can be represented as like pixel value, okay? A1, A2, A3, A4, A5, A6, A7, A8, A9. Now, if I have an image with 9 pixels, and that 9 pixel can be lined up to become non-dimensional vector. I can put a 9 here, all right? So this is called low measure storage or low measure representation of image. Originally, you have a 2D image. Now I have a vector, it's 1D, but the number value is still the same. Here you have 9, here you have the 9. Understand? So don't worry about this 2D or 3D. You look at individual values, then those values are represented in a vector. So it's just longer, all right? You have a 9 value here, you have 9 value here. This is called vector representation of image. All right? Not very difficult. Keep that in mind. This is could be intensity, brightness of the pixel, or could be RGB. For RGB, then each RGB value in the pixel, you have 3 values. It becomes longer, all right? Like this one becomes 3 times as long, all right? This is like you have 3 values here, you put it together, it becomes, instead of 9, you have 27, all right? Here, 27, if you do RGB, all right? Then suppose I have another image called B, right? I have another image B, B1, B2, B9. Now my question for you right now is that how we can compare the similarity between A and B. Before we have symbol, right? Symbols that they are the same or different. And with they have certain similarity, then it becomes harder. I say, forget about it. I just look at the image. Now I have a vector A and a B. So want to see the similarity between A and B instead of symbol A and B. I repeat again, it's a little bit simple, but very difficult to understand the importance. I'll go back again. Originally, I have a and B, and they're just same or different. Now I represent image because the image is what you get from real world, all right? Then I say vector A and B, how they are similar or different, all right? Then I do some operations. I want to subtract. And before subtract, I want to do average difference, all right? I want to take out average. I do average first. I do average value that called brightness. Just brightness is more intuitive, all right? Brightness sometimes called the mean, all right? Mean of the value. So I use bar. A bar is a value that add all these values together. So A1, A2, A9 divided by 9, all right? And in general, does not have to be 9. Could be like 1 million, right? This is like 1 million, this is like 1 million, right? I use actual numbers there so that it's easier for you to see. And later on, you know, the 9 does not have to be 9, like 27, for example, I already had 27, all right? Now, B. B bar is B1 plus B2 plus plus B9 and divide by 9. So that's average, right? So average is like average intensity of this image and average intensity of this image. And I want to subtract mean. Subtract the mean. And when I subtract mean, means that I do not care about how bright that image is, all right? Because brain is really good because your eye can open when it's dark and your iris will close when it's bright. So your eye really do not see much the brightness. So I really disregard this one automatically. So let's just subtract it out, all right? So I called A prime is subtracted out. 1 minus A bar, A2 minus A bar, A3 minus A bar, A9 minus A bar. That's called prime. Prime is subtracted out. A B vector also subtracted out. B1 minus B bar, B2 minus B bar, B3 minus B bar, B9 minus B bar. So each image gets subtracted out, all right? Then if you do this, this vector has a zero mean. What does that mean? If you average all this value out, you get 0. B prime has a zero mean. If you average this factor, you get 0. Why? Because mean already subtracted out. All right. It's called zero mean vector. All right. Prime is a zero mean vector. All right. So we can call zero mean vectors. That's what we define. All right. So any questions? Now, first step, we subtract the mean out, and we call it zero mean. All right. That's motivated by the brain. All right. Any questions? That's the first step. The second step, we want to disregard contrast. Disregard contrast. Contrast is how contrast, what's the contrast in your image. So we call the U is a function, and we convert the A prime, that's already zero mean, so that original vector has zero mean. I divided by the length of that vector. And what do you mean by length? All right. So you suppose I have a vector. You probably already learned, all right? A1, A2, da da da. I have a A9, and the length in Euclidean norm is the summation of all those components, all right? Da da da. A9 square, and I take the square root. That's the length, all right? So now after doing this, I will say that U, A prime star, length becomes 1. And we called it A0, all right? And U, B prime, that vector is 1. We use a notation called B0. All right, so now this one has zero mean because we subtract mean out first. Then we have a unit length because the length of this vector is always 1 because you compute that one and you get the unit length, all right, unit length. So summarize again, all right, we have 2 steps. First step is we subtract mean. The second step, we disregard the contrast by dividing its length, all right? All right, so it's simple. I'm pretty sure that you learned that in the linear algebra, all right? Because the subtract mean, you learned that, and subtract the division by the unit length, you also learned it, all right? Now, we talk about distance. That's also nothing new actually, but it's beautiful. We want to talk about distance between such two vectors, between A0 and B0. How do we do this? All right, and the way we do this is really easy. Really easy. We have a mathematical we say the distance between A0, B0 is the inner product between A0 and B0. And that dot is inner product. And we learned that in calculus, all right? And let's see what that means, all right? We'll just review a little bit, all right? Let's review a bit and write it down, our definition, and we talk about the meaning, all right? Inner product. Review, all right, still review. inner product suppose have a vector A1, A2, A9, inner product with B1, B2, B9, and that equals to A1 times Z1 plus A2 times B2 times A9 plus B9. That's inner product, all right? Just add this together. So now what's the meaning of this value? Because A is zero mean and univector. This is also zero mean univector. And then we have something like that. This one in the product of this B equal cosine theta. Originally, if you multiply any vector A with any vector B as in the product, then you have a cosine theta, but then you also have length of A and the length of B. But length of A, length of B equal to 1, so they're gone. We have only cosine theta. Then what do you mean cosine theta? Let's draw a picture, all right? And suppose I have a, this is like A0, B0, and you have a theta. Then, and this is A0, this is unit sphere, unit sphere. That's unit sphere. And the angle between two unit vector is theta. In the product is cosine theta. And what do you mean cosine theta? Cosine theta is like that. All right, theta. Then we have a pi. We have a pi over 2. Nothing new here. That's high school stuff. All right, this is 2 pi, the 2 pi. And that's a value. That's a value like 1. That's minus 1. And I draw cosine theta. All right, draw cosine theta is like this. Ooh, ooh, ooh. All right, I didn't draw it as well. I should draw more symmetrical. That's what we learned in the high school, right? So you need to thank your high school teacher, cosine theta. So cosine theta will be like this. So basically, when the angle is close to 0 or 2 pi, it will wrap around, it continue up, and the value is high. So when the angle is larger, then drop, larger, then become to negative once it go to go beyond 90 degrees. So if this angle is close to 0, then the value is high. So we just use that value to measure the similarity between these two vectors. I repeat again, we use the inner product of zero mean unit vectors to get a cosine theta, then no matter how big that 9 is, could be really huge, millions in brain, 250,000, right? Because each neuron is so big, it have 250,000 connections. It doesn't matter. And it just use that value. That value we'll talk about this next, all right? And talk about brain is beautiful, beautiful, all right? So let's do next. Once you have a cosine theta as the inner product, all right? Then we compute, this is called neuron with weight, all right? The weight is a vector, V, and the input, suppose neuron has the input of X, right? And the pre-action potential means that he tried to detect pre-action potential. That's our model. It's approximation, right? Pre-action potential is V0 in the product of X0. This is going to be like millions number, all right? Z to inner product, all right? Then this is the power of a neuron to compete with other neurons. We'll do that later on, all right? The pre-action potential will be used to measure how well this neuron will fit. The V is a fitting X, all right? And we'll get that, all right? So now we move on to FA. Are you ready? I'll review again, all right? We convert each vector, image, or weight, this is also vector, into zero mean and unit vector. After that, we do inner product. And the inner product of two zero mean unit length vector becomes action potential of the neuron. Then in different neuron, we have different V. And different neuron, we have the same input. And we'll see which neuron V will match X better. That's through competition, all right? Any questions? The next I will relate to FA. Beautiful area. The FA is the, if FA is a symbol originally, right? We have a transition symbol Q, sigma, this is a state, this is input, we'll go to a new state, all right? And delta is a function that map from all the possible Q, that's all possible sigma, all right? And that will map to the space of Q prime, which is also Q, all right? So the lookup table is like that. That's our lookup table or transition table, same thing. So suppose I have a Q1, Q2, Q3, Q4, Q5, Qm. And I have input sigma 1, sigma 2. Normally, we have only A and B, but suppose I have more, all right? I have a sigma I, I have a sigma N. And over here, I have a say Qj, right? So when we have a lookup table, we want to compute that this one, what do we do? We say, look at it, oh, from Qj, and sigma I, over here, I have a Q prime. That's exactly that one, all right? And we don't want to use a Q prime. Maybe I call it QK, all right? So from Qj, sigma I map to a new state called QK, all right? So I probably take that out, all right? QK, so now IJK, all right? And the lookup table is that I look at symbol exact, match or didn't match. Then I will link to the next state. And the next, I want to use our, no, before I write it down this way, so delta Qj and sigma I will becomes QK. That's a general with IJK. IJK is the number, integer. Because we have a finite number, we have finite number, we have finite number here. All right. Now from here, we want to link into the neural network. That's beautiful. All right. Not very difficult, but it's beautiful. Next, I will talk about inner product, and instead of a symbolic match. All right. So are you sure you are ready to take the excitement? All right. EFA. We have 2 steps, all right? Emergent FA, you have 2 steps. 1, all Qs, symbolic Qs will correspond to, corresponds to vectors, all right? So each Qi, I use this called equivalence. you map to a vector zi. All right. Originally, this is a symbol. I will be equivalent to a vector. All right. For Q is a state, I will call the muscles. Muscles, those values inside the value is each value inside the vector corresponding to your muscle. Like this could be like thousands. Thousand muscle when I speak and I start to issue those vectors start to drive my vocal tract and also my vocal cord, pressure in my lung so that I start to speak, all right? So this is a lot. This is also a lot, all right? But this could be like huge number. The number of vector dimension is low, all right? Suppose I have say 1,000 muscles, so this dimension is low. But 1,000 muscles can generate many symbols, a huge number of these symbols. But with that one, I don't need a symbol anymore. I just speak. When I was a baby, I just cry, I make noise, and that corresponding to vector here, but I will not do this one because my mom did not know this. Right? Mom did not have that one, right? The second step is that all sigmas, g's, corresponding to also vectors, sigma I will corresponding to, oh, that should be sigma, all right, QI, corresponding to xi vector. That's called image on your retina or on your cochlea. So sigma is the input. Input is from your eye, from your cochlea, all right? Those are your cells in your eye. These are the cells in your muscle, all right? Now, these two steps. After the two steps, I get rid of this one because this one requires human intelligence. This one, I will construct machine intelligence. I just take Zi, Xi directly from the real world. This from your eye, this is from your muscle. When you cry, you are practicing, you are generate FA, all right? So suppose originally FA, you have delta QJ sigma I will go to QK. That's our handcraft, right? In our class, we are doing that so far. In fact, all you are doing actually in computer science is the department, you are doing this, called symbol, all right? Now, EFA is a revolution, all right? EFA said that doing automatic, and you want to say ZJ, XI will go to ZK. Aha, beautiful. This is vector, vector, vector. Symbol, symbol, symbol. Once you have a symbol, you never be automatic. With muscle, images, and muscle, and you are doing everything automatic because you don't have a human in the loop. That's our called brain. Brain transition table. Brain, all right? And that's a simplistic way of putting it because I don't want to make it too complicated so that you understand it, all right? So now how do we do this? We're still doing transition table. Instead of symbol, we do vectors, all right? Then write it down how we can do it, all right? So neurons, want to do this. Suppose I have a transition table, right? I have a Zi, that's in the row, and J in the column. That's our transition table. And that has a template for the transition table. And that I called weight IJ. Is vector, vector, vector. And that I called neuron inside the brain. That brain has a YIJ and has a weight. Neuron has a weight, WIJ. Put together, this is like 1,000 dimensions. This is like 1 million dimensions, and the whole thing is like 1,000,000 and 1,000. The landed up 1,000 number, 1,000,000 number. Then I call WIJ. That each neuron will have different weights, and a part will match state, a part will match input. Because lookup table have two components, row and column. All right. Then suppose originally I have input for FA, right? Input for FA will have Z, X will map to Z prime. That's our lookup table. And that one, now I have a vector, the EFA. They have a ZX go to vector. And that one, this part I call it P. P is putting this together. Put the state vector and the input vector together. Now, I already called the inner product, right? So I called, we already have pre-action potential. Pre-action potential, we already said action potential. And of neuron, YIJ with weight, WIJ, right? Then I do this is equal to ZI multiply the Z part in the product, this is in the product, plus XJ, which is the weight in the product with X. So I have two parts, right? This one is the Q part, state part. This is the sigma part, which is the input part. For lookup table, lookup table, transition table, I need this match and this match. Now already doing this, did you remember we do in the product? So look at the value. The value, look, the pre-action potential to is bigger now, all right? So with the is, I will say that is this, all right? Is this. Then I have drive something really beautiful, all right? Suppose now of X, that's like retina.
Excuse me, Professor.
Yeah,
Is the second X in the sigma place supposed to be a vector?
yeah, thank you.
No
This
problem.
you fetch very well. Just let me remind you, everything's a vector. This is not, this is not, this is out of vector, all right? And the Q corresponding to this. Q corresponding to this. Sigma corresponding to this. Before we don't have this. We don't have this. Now we have a weights. And then we have this. The neuron has this is this. And we use in the product to see how we'll match Q and sigma. Before we are doing table, transition table, we just use symbolic, and the machine does that, but not automatic because using symbols. Now we do this, right? Now, hey, that's your brain, your beautiful brain. Brain like this, Then I have a muscle. Muscle is on your body, Just a muscle, your limb, your mouth, your legs, and this your retina, and could be your ear, all right? Then you have X coming in, and you have a Z come. This is difficult to understand. The muscle actually, when you speak, when you cry, this vector Z will come in, all right? This is Z area, this is X area, and its value will be Z vector, right? This come in, and we have so many neurons, all right? I have neurons, Y11, Y12, Y13, Y21, Y22, Y23, and da. I have Yij. I have trillions of neurons. I have so many neurons. Simplistic way, I only link this X to all these vectors. All right, this the neuron Yij. All right, this is Yij. I use vector. All right, each neuron has a lot of input weights, and this is Yij. The Yij and has more than that. All right, Yj actually not just this weight, but I only talk about weight. Later on, you will see the age, how old this neuron is. So this vector is larger than this vector. But for simplistic version, we just said that Wij. That's all you have in there. All right. Then you have so many neurons, and I use Ij because the transition table has row and column. All right. So transition table has m rows, suppose I have m rows and n columns. All right. Suppose I have m rows and n columns. How many neurons you need? M times n. Why? Because each row need a vector like xj. No, each row need a z actually. And then each column need a xj. And m row, each row need a zj. Then you need m and n put together. You need a m times n for the FA. Then you match all the possible row and column. So that this guy will fire. I'll get to that. All right. And the matched column and rows, this neuron will fire. You say, hey, guys, and I'm the best match. All right. So we need to do competition. I'll write it down. Competition. All right. Competition like market economy, you need to do competition. All right. We need to do top K. And in simple case, just K equal to 1. All right. Simple case equal to 1. Then you will find argument of max value among the IJs that has a P that one, right? P, I put a 0 there because you want to zero mean in univector in the product that W IJ that also unified. All the IJ with XZ input, X from I, Z from muscle, and you do inner product and you find which IJ will do the max. If I find a max, then I have a star, J star. I's row, J's column corresponding to the best match. So now I convert everything into vector now. I'll recap again. So we are at the home row, all right? So we already have, originally have symbol and symbol, that's a dead end. Now I have images, I have muscles. Then I use neuron. Neuron has the internal representation, which is the Wij. Those are the weights. And those weights will match exactly corresponding to the vector of the retina and corresponding to vector corresponding to Z. Then it will match perfectly and see which value is higher because this one is called pre-action potential. And if this guy is the max and we make K equal to 1 mean that only one single guy will fire. K equal to 1 that this top one will fire and this fire, all right? This guy, suppose this guy fired, all right? All the losers don't fire, only one guy fired. And this guy fired, and I have a connection to here. This guy fired that Z has input from this area too. And this area say which neuron will fire here. If this neuron you have here, say 0, 1, 0, then this neuron start fire. This neuron will link to this neuron. Boom, linked. All right. In fact, depends how often they're linked. This one is probability. This is the detail. Don't worry about it. All right. So basically, they are linked. The 5 neuron will link to the 5 neuron here. If this neuron is firing, and it will be linked. Maybe this neuron is also firing, this neuron will be linked. So it's perfect. If this neuron fire will only link to the neuron that fired, then this 0, 1, suppose you have 0, 1, fire not firing. This is called spiking neuron model. Then the neuron will fire. Then you start to speak very sophisticated language, like English, like Chinese, all right? So you need, in simplistic case, you have mn neurons for FA, for the FA. That's it. For FA, because input is all pattern fixed, you just need a finite number neuron, m times n, m rows, n columns, all right? This is the simplest fashion, but in real world, it's not like that, all right? In real world, this is different, all right? This is changing all the time. Then the winner will fire, all right? It's like you see your little sister, and she look like similar. Why? Because this neuron will link to sister. This put together will be sister. So you have a father, and a father image coming up, then this neuron fire, then link to father, then you start to dad, right? So this is a very, very intuitive way of explaining how the brain does, all right? So now, then the EFA is doing APFGP. That don't worry about it. APFGP is not, but at least is doing FA. Later on, that will be general purpose, but actually right now it's still FA, all right? By a living machine. And I sent Ronnie Brooks to MIT at that time very early. It's called living machine, because the robots like living machine. It learns, and EFA, then you have eye for images, have a muscles, then link together, then start to link. And in fact, something really interesting is that if you can predict input, right? Suppose this is also neuron, then this can predict your input. It's like mental image. You expect what you see, all right? So you can get this one, and window will fire. Window fire will predict next pattern, all right? And how do you learn? And learning has to be automatic. You cannot just handcraft. So the heavy learning. All right, heavy learning goes like this: Z, X. I have a neuron. The window will learn and put that input in, and then put this input in. All right, and then I have a Z and X. That's next time. T minus 1. I put a different time now. All right. So this is the previous time. You have a muscle and X and link to this one, and this is winner will link. And at time T, and the next time that I should go forward. Always go from left to right. All right. This is because this is T times 1. We will T. Then this will go to predict next X, which is here. Next Z is here. So this is time. All right. Then you start to have a boom, boom, boom. All right. And we are almost done. And I'd like to give a quiz. All right. The quiz said that I will add a little bit next time, but I'd like to do a quiz first, all right? Because I already finished everything except the example. Next time I will do example, all right? And let's do a quiz. To complete the NFA, all right, below 1, 2, 3, completely learn, error-free. That's a double circle. Sigma equals A in B. I use EFA. How many neurons do we need? In EFA, we need. I write this one. Did you remember? How many? How many states? 1, 2, 3. How many input symbol? A, B. Anybody want to try? How many neurons in FA you needed to be perfect?
Is it 6?
Yeah. Why 6?
2 times 3?
2 times 3. Yeah. 3 states times 2. Thank you. So let's do a quiz. All right. Let's do I'll give a little more time. Go to the go to the 40. Go to Google Classroom. Do you see that quiz 6? Do you see quiz 6? Go to Google Class.
Yeah.
All right. You give the number of neurons for the EFA. All right. Any objection about the 6? 3 states times 2 simple impossible. 2 times 3 or 3 times 2. Objections? We already see 10 people hand it in. Any questions? Congratulations, we did it. Thank you. Class is over. Bye-bye.